All right, welcome everyone. When managing a set of distributed assets, like in this case, wind turbines, it can be really challenging to answer questions about these assets in aggregate in real time. Questions like, how much power are these assets producing right now? And why are those questions so difficult to answer? Well, this is a distributed system, so messaging is inherently eventually consistent. And what we need to do in these kind of aggregations is represent that uncertainty. So we need to embrace the eventual consistency, but somehow say, here's our aggregate, but only 99% of the assets that we expected to be reporting have reported, and the other 1% is uncertain. These aggregations can also be quite dynamic. So in the wind turbine example, again, you might want to have an aggregation for a single farm, or all of the assets in a certain county or state or country, and be able to zoom in at different layers of that hierarchy in real time to provide context. And of course, this can be really, really challenging if your assets are moving, like in the transportation industry. So these applications, they go far beyond just data ingestion or pure streaming applications, and they can't really be siloed off. They interface with a lot of other business systems, and they're really used for making operational decisions or even doing closed-loop distributed control. Now, these systems aren't really new. These systems have been around for a long time, like in oil and gas or electrical transmission and distribution, where you have streaming telemetry mixed with rich asset information and relationships, and those relationships changing over time. This is where I've spent my entire career, approaching 20 years now, is working on these types of systems. What's changed recently are we're building these systems on top of cloud services now, and they're much, much larger scale. And I think you can make an argument, too, that they're much, much more dynamic now on top of open source technologies. So in this talk, I'm not going to talk directly about any of the systems that I work on. I hope someday that I can, because they're quite interesting. What I'm going to talk about are the building blocks for building these types of systems that I mentioned in the introduction. And I'm going to return to this wind turbine example throughout, just so that we have something concrete to talk about. This is also not a technology agnostic talk. I'm going to talk about using Akka and Akka streams for building these types of systems. All of the examples I'm going to show are in Scala, but even if you're not familiar with Akka or Scala, I hope not to get lost in the details. I'm going to show a lot of examples, but what I want you to take away are the high-level messages in terms of the challenges of building these systems, because you're going to need to face them whatever your programming language or toolkit is. So because the presentation is kind of dense with examples, I'll just give you a bit of a roadmap. I want to tell two stories. The first story is a motivating example for using the Akka Streams API, and it's really a story about actors not being sufficient for processing pure streaming workloads. If you're not familiar with actors or streams, it'll provide a bit of an introduction to the two, but even if you are, what I hope to do is tease out the distinction in terms of what actors are really good at and what streams are really good at. And then the second half of the presentation is kind of putting them back together and taking the strengths of the two and marrying them together in a complementary way to build the types of systems that I mentioned in the introduction. Okay, so let's start with a motivating example. Let's say we have a fleet of wind turbines, and we want to build a web service that will collect telemetry from those wind turbines in real time and store that telemetry in a database so that it can be queried and used in other applications. And each one of those wind turbines is going to have its own WebSocket connection that's unique for streaming the telemetry. So let's build a proof of concept service using Akka actors. So the first thing we'll do is create an actor that's going to maintain our connection to the database. So if you're not familiar with actors, actors are really just a class, and you interface with them through messaging. And in this case, we'll hold the database client inside that actor, and every time we receive a new sample to insert into the database, we're going to call this asynchronous database message to insert the sample. And since it's just a proof of concept, we're going to ignore errors from now, and we'll return to that later. We can create the database actor as follows, and then we can use it in this WebSocket stream, which is in Akka HTTP implemented with the Akka Streams API. So this is a stream, and within that stream, we can send the database a message every time we get a new sample. Pretty simple. Now, the first thing we run into when we start testing this proof of concept is that the performance is really poor because we're sending a single sample to the database one at a time. So we need to introduce some kind of grouping to improve performance. OK, so we're smart programmers, so we can program our way around this. And the actor is great for capturing this mutable state. We'll maintain a list of samples and the number of samples in that list. And each time we get a new sample now, instead of putting it in the database, we'll append it to the list and increase the count by 1. And if we hit 1,000 samples, then we'll insert it into the database in a batch using a bulk async insertion. And then we'll zero out the number of samples queued in memory. Okay, now the problem with this is sometimes the rate that we're getting messages can be quite bursty. And so there's large periods of time where we don't get any messages. And if we want all of the messages in the database to be as near real time as possible, we need to have some kind of periodic flush to keep them timely. So we need to add a periodic event, which is, again, really easy to do with an actor because there's a built-in timer. So when we start the actor, I'll just set a tick to send ourselves a message in 1 second. And when we get that tick, we'll insert into the database and then schedule another timer for the next second. So this, every second, will at least flush what we have in memory. Now, we know this to be true, of course, but sometimes it's really hard to resist, right? So the one problem with introducing this periodic flush is we batched all these messages in memory to improve performance, and now we've introduced this timer, and the timer could fire right after we just completed a batch, and that kind of drives us crazy. So this is getting hard to read now, so I'll zoom in. Add another variable to keep track of whether we've flushed events in the last interval. And if we have flushed events, we'll set it to false. And when we come to our periodic timer, if we've inserted within the last second, well, then we'll just skip that insert. OK, so the next problem we run into as we test this proof of concept service at scale is we notice that we can overwhelm the database with writes, with these asynchronous writes, and actually degrade its performance such that it impacts other applications. So somehow we need to rate limit these requests. And again, we're smart programmers, so we can program our way around this. We'll just add one more variable and count the number of outstanding requests to the database, and we'll never let the number of outstanding requests exceed 10. Now, of course, if we want to keep our batches at 1,000, that also means that we now need to manage that queue in memory and split them at 1,000 and keep track of what's remaining, and so on. When the bulk insert does complete, we're going to send ourselves a message to decrement the counter, and when we receive that message, decrement the counter. And if we have more than 1,000 events in memory, we'll send those to the database, and of course, we can't forget to set the flush variable to false. OK, so how does our proof of concept look? We started out with a nice little actor. Felt pretty good. Insert samples into the database pretty easily. And now we've ended up with this. And if I zoom in on the insert method, it's not even really clear on first glance what this does. In fact, I'd love if there was a bug in here, because it would help prove my point. So we've seen that the actor's good at managing mutable state. And it's been good for thread safety. We haven't had to worry about locks or threads or anything like that. And the timers were certainly easy to use. But if we kind of zoom out, we're having to encounter all the same old multi-threaded system programming problems that we've had to deal with for years. We're having to manage concurrency, manage memory, manage flow control, these kind of things. And if we look at the testing for this actor, in terms of making sure that it's doing what we expect, that's going to be non-trivial. And of course, we ignored error handling in this proof of concept to begin with. So if we need to introduce error handling, that's going to complicate our implementation quite a bit, especially if we need to maintain order in terms of the samples, because remember, it's a streaming application. So anytime you have error handling and ordering, that can be quite challenging. And then we've taken care to throttle the number of asynchronous writes to the database. But of course, we've done nothing to throttle the number of messages coming into the service from all the wind turbines. You get the point. So in order to throttle the messages, we'd have to implement some kind of acking and messaging and tell the wind turbines to slow down. And of course, that's going to be basically inventing a protocol to implement back pressure. So our proof of concept actually looks a little shattered. So I quickly want to look at the Akka Streams API, and then we'll revisit our proof of concept. So the Akka Streams API was really built in response to these challenges. That's why it exists, basically. And the Akka Streams API, really importantly, is a high-level end-user API that's built on top of the Reactive Stream specification. I think that's something that I really love the Akka Streams API. I'm a huge fan. A lot of people, they embrace the Reactive Stream specification, but it really should be just for library developers. Akka Streams API gets it right as being a high-level implementation that we'll see some examples of here in a minute. So Akka Streams API, very briefly, there's this notion of sources, which just emit messages. They don't have any inputs. Sinks, which accept messages and don't have any outputs. There's these elements that can perform transformations like mapping and filtering, so they have messages coming in and messages going out. And they can be composed into flows in more simple cases like an ETL application, or in more complicated cases where you need to merge streams or bifurcate streams, they can be expressed in terms of graphs. Now, one of the really important parts of the Akka Streams API is this notion of back pressure. And it's also, back pressure works basically by the downstream asking the upstream for it to send new messages, and that way the downstream can never be overwhelmed by a faster upstream. And it's also quite efficient because it happens asynchronously and it's also batched. Okay, I just want to briefly review, there could be a whole talk on this on its own. I just want to briefly review some patterns that we've seen so far for streaming telemetry using the Akka Streams API. So the first is grouping. And Akka Streams API has a group stage, and it'll emit those batch up messages and then emit them in groups. And of course, like we saw before, we have this problem that sometimes we don't want to wait for a complete batch. We want to emit based on a schedule, and there's a grouped within stage for doing that. In terms of rate limiting requests, say like an asynchronous request to another service or an HTTP call to a database, map async is the way to limit these, and just by adjusting the amount of parallelism, you can control the number of outstanding asynchronous requests. The other really important thing about map async is that it emits downstream in order as well. So this is something if you're just managing streaming workloads with futures alone, and you need to maintain order, that can be quite challenging, and map async will handle that for us. And one more pattern, throttling, you can have upstream messages be much, much faster than downstream messages and emit on some kind of schedule. Okay, so let's review our proof of concept in light of the Akka Streams API. So in our original implementation, we have this WebSocket that's receiving samples from the wind turbines and then sending them to the database actor that was doing all of the heavy lifting. And that entire database actor can be replaced with these two lines of code from the Akka Streams API. So the first stage is going to batch up messages into groups of 1,000, but it's not going to wait any longer than a second to emit messages that it has, even if it hasn't completed a full batch. And then the map async stage is going to limit the number of outstanding requests to 10, and it replaces all of this code that we had in the actor before with these two lines. And we've seen that like some of these things are conceptually easy, right? Like a grouped within is conceptually easy, but once we get into the implementation details, we see in the actor there that it's non-trivial. And the actor implementation, of course, was going to be a burden to test. Here, I don't feel I need to test group within or the behavior of map async. I trust that the Akka team has done that for me. And one of the things I really like about Akka Streams API is you can actually test these streams basically from end to end in unit tests. There's a great test kit for doing that. And of course, we can take advantage of some patterns in Akka Streams for doing error handling. And this stream is now fully back pressured. So we have bounded resource constraints, and we can also adapt to very dynamic workloads. So our proof of concept actually looks pretty darn good now. What's shattered, I think, now is our faith in actors. And I've seen that actually go as far as some people to to question, why do we even need actors now? We'll just use streams everywhere. So what we've seen is that actors alone aren't sufficient for handling these streaming workloads, especially unbounded streams. But it turns out that the two are actually quite complementary when combined. Any Monty Python fans? All the people I work with are too young. They don't know who this is. Okay, part 2, about putting actors and streams together to basically have the building blocks for the systems that I described in the opening. Okay, so the first thing is bridging actors and streams. So how do we send messages from a stream to an actor, or from an actor to a stream? So if we have this flow, and we want to send a message to an actor, that might be some kind of intermediate result, and we can send it to the actor to maintain that state, or as a place where some other service could query it, because there's no real means of querying a stream, but of course you can easily query an actor. So the way to do this safely is to combine map-async with the ask pattern. So in order to show this example, consider this really simple actor that just maintains a sum. So it has a member variable that keeps track of the sum. When it receives a new increment message, it's just going to increment the sum with the value. And it also supports a query so that you can query the current sum. Instantiate the actor like this, and then we can use it in, again, I'll use a WebSocket flow that's getting some messages, and we'll just increment the sum by whatever the new sample is. Now, this isn't safe, because the tell method with the bang, that's fire and forget. So essentially what we've done here is created a discontinuity between the safe back-pressured world of the Akka Streams API and sending a fire and forget message to an actor. So we can overcome this by, in the actor, when we receive the new increment message, we can actually respond to the sender. And once we have a message in response to the sender, now we can replace this fire and forget pattern with the ask pattern, with the question mark, and we can map async over it, and that's not going to emit downstream until that future is actually completed. And now we have back pressure through the entire stream again, and this is safe. The other way to combine actors and streams is to use the actor as a sink. So that's basically embedding the actor right in the stream as the sink. And this is similar in flavor to the actor we had before. It's just a little bit different in that it needs to have an initialization method to handle the subscribe. And then similarly, in the increment, it has to have an acknowledgement like we were replying to the sender before. But we don't need to modify the query, because the query is not going to be used in the stream. The query is still going to be used externally from some other client. So you don't have to have any notion of acknowledgements or anything there. You're returning a message anyway. You can instantiate that actor, just like we did before, and now we're going to wrap it in a sink. And as part of wrapping it in a sink, you say what the initialization message is and the acknowledgement message. And then the sink just gets embedded right into the flow, and the stream itself will handle sending messages to that sink. Okay, so what about the opposite? How do we send a message to a stream? That can feel a little bit like this when you first get started. Once you have messages in the stream, you're comfortable with mapping and throttling and all these different patterns, but how do you actually get the messages in there? So one way is through the Alpaca project, which is part of Akka in terms of interfacing with in a reactive streams way with lots of other systems. One of those being Kafka, but there, Cassandra, S3, all sorts of different things. So if you're consuming off Kafka, if that's your source to your stream, well then the answer is easy. You need to produce messages into Kafka on that same topic, and then now you're going to have messages into that stream. But what if the stream is just running in the JVM? How do you get messages into it? The first way, there's two ways to do this. First way is source actor ref, which basically you can materialize a source into an actor reference that you can send messages to. So from somewhere else in your program now, you can just send a plain old actor message in order to get the message into the stream and then part of your streaming workload. But as we just saw, this fire and forget approach isn't safe because we have the discontinuity with back pressure. So there's also source queue. And source key will materialize into a variable that has an offer method that returns a future. And now we can put this into a stream and map async over it, and it's safe. You have back pressure. OK, so that's basic messaging between actors and streams. Let's take a look at actually encapsulating streams inside actors. So here's a simple actor that just prints a bunch of numbers. And it has a member variable that is a stream. So there's a stream actually running as part of the actor. And this stream is just going to print the numbers from 1 to 5. And then when the stream completes, it's going to tell the actor stream complete. And when the actor receives that message, it's going to print a message to the console and then stop. And when we run it, we see what we expect, the numbers from 1 to 5, and then the message stream completed. Let's look at a little bit more detail in terms of stream management, though, in terms of actors. Let's say that that stream is unbounded. So this stream is just going to emit a new value every second. Again, just print it to the console. And when the stream completes, it will tell the actor that it's done. But essentially, this stream is going to run forever. I'll also add a receive timeout to this actor. So if the actor hasn't received a message within 5 seconds, it's going to get a receive timeout message. And when it does receive that, it's going to print to the console so that we can see it and then stop itself. And if we run it, we see what we expect. The numbers from 1 to 5, and then the receive timeout message, and then the actor stops. But in this case, we created the materializer for that stream inside the actor. But of course, materializers can be reused. So if you're reusing the materializer and you're passing it inside the actor, what you'll see is the numbers from 1 to 5 are receive timeout. The actor is going to stop, but the stream's going to keep on running, essentially, until the materializer is stopped. Because the stream's actually not, it's important to remember the stream's not running like inside the actor. It's running on the materializer, so they're independent. So the way to handle stream management in this case is through a kill switch. So you can materialize a stream with a kill switch, and then when you want to stop the stream, you just shut down the stream using the kill switch. So if we run in this case, we see what we expect. Numbers 1 to 5, we get the receive timeout, we hit the kill switch, which stops the stream, and we see the stream completing. Okay, what about like industrial scale stream management? Let's return to the wind turbine example that we saw before. Instead of focusing on the service, the proof of concept service we built, let's take a look at the wind turbines themselves, and let's build a simulator for a wind turbine so that we can test our service. Now, a WebSocket client in Akka HTTP is just a flow. Messages in, messages out. It's very simple. And let's use that to simulate some JSON message that represents the current samples for that wind turbine. And this is the graph that describes our WebSocket simulator. Every second, we're going to generate a new random sample expressed in that JSON message. We're going to send it over the WebSocket to the service, and the service will store it in the database again. And for any messages that we receive back from the service, we'll just print those to standard out. Now I want to focus on like the life cycle events of this WebSocket stream. I'm not going to go through them all. I just want to pick one example. So when the WebSocket stream gets a connection established, it's going to send a message to an actor that's going to act as its supervisor, telling the actor that it's connected. And similarly, if it fails to connect, it'll send a message saying that it failed to connect along with the exception. Now, I realize this is a lot of code. Don't get caught up in the details. I just want you to get a high-level picture of how the actor is being used to supervise the stream. So this is a wind turbine simulator actor. And inside it, it's going to host a member variable, which is the WebSocket simulator stream that we just saw. And in terms of those lifecycle events, when it gets a connected message, it's going to print a message to the logs so that we can see that it's been connected for traceability. And then the actor is actually going to change its behavior and become running using the become method. And once it's running, if that WebSocket stream ever terminates, the WebSocket stream is going to send the actor a message saying terminated. Again, we'll log a message for traceability. And the supervisor actor is going to throw an exception and let its parent restart the actor. And as part of restarting the actor, we'll restart the WebSocket stream so that it can reconnect to the service if the connection's ever lost. And similarly to, like we saw in the previous example, if this actor is stopped independently on its own, it's going to use the kill switch to stop the WebSocket stream from running. Now, it's really easy to spin up a whole bunch of simulators to test our service. So you can spin up 1,000 just like this. Now, it's a little resource intensive. Probably get like a TCP SYN flood locally or something like that. So we'll throttle the startup a little bit. But who knows how long to sleep in this kind of case. So this is another case where you can actually go and reimagine a workload that's not typically streaming as a streaming workload. So let's use the Akka Streams API with the nice throttle element to throttle 100 actors at a time and then start up the actors that way, rather than just having some kind of magic sleep. Okay, so what this looks like visually, we have like these 1,000 wind turbine simulator actors running under the user guardian actor, directly under that guardian actor. And of course, if we lose our connection to the service, we get this kind of denial of service from all of these connections being restarted in a tight loop through the default actor supervision. So I want to take a very brief look at stream supervision and then return to actor supervision to solve this problem. Stream supervision is really about messaging. So it's not so much about the life cycle of the stream itself. It's more, consider an application that's just doing like ETL and parsing messages. You might get a message parsing error, so you're just going to log that for traceability and then drop the message and keep going. And then if you say got an exception that you didn't expect, maybe you want to stop the application so that you can investigate. But we need some notion of backoff supervision in order to handle this case of reconnecting to the service. So it's actually fairly easy to do, and there's two ways to do it now. The Akka Streams API in the last release, I believe, a couple months ago, introduced a backoff source, which can be used to do this. I'm not going to show an example of that here. What I'm going to show an example of is using the actor backoff supervisor, which can often be more valuable if you have side effects that you have when you're restarting a stream. Like you might need to reset counters or send a message to some other service, these kind of things. It's easier to handle in an actor. And it's this easy to do, is you're just going to insert another layer of indirection through the backoff supervisor actor, and then the backoff supervisor actor will start up the simulator. And of course, the simulator actor hosts the stream that's actually simulating the messages. And note here that we didn't need to modify any code in order to do this in terms of the actual simulator. And the picture changes from this, with all of the simulators running directly under the user guardian, to having a backoff supervisor managing each one under that user guardian actor. Okay, what about distributed stream processing? So Akka Streams API is a local abstraction. It doesn't have a distributed materialization. But actors can be clustered and, of course, distributed across a cluster. So we can leverage actors in order to distribute streaming workloads. And one of the ways to do this is through Akka cluster sharding. Now, cluster sharding is the idea of taking a large collection of very similar actors that are going to consume more resources than one server might have in terms of CPU or memory or I/O. And you're going to distribute them across multiple machines. You might also want to do that even just for resilience so that you can lose a machine and keep running without interruption. And so what it looks like is this. You need to have some way to create a shard ID. And from that point forward, Akka cluster is basically going to take care of the placement of those actors for you in a transparent way. The programmer doesn't really care, and even in terms of operation of the cluster, you don't really care. So let's look at how we can leverage this to run streaming workloads. I'm going to introduce one more layer of indirection through a wind turbine supervisor actor. And when this actor starts, it's going to send itself a message. And when it gets that start message, it's going to create the backoff supervisor that we just saw. And then under that backoff supervisor, we have the simulator actor and eventually the stream. And then if this actor receives any messages, it's just going to forward them on. And then the way we actually create cluster sharded actors in a cluster is just through an actor reference. It's really quite simple. You need to tell the cluster sharding system how to create that actor. You need to tell it how to send messages to it, and I won't go into details of that here. And you need to tell it how to extract the shard ID, which in our case here, we have some unique identifier, take the hash code, and modulo the number of shards. It's really that easy. And then to spin up many hundreds or thousands of actors in an Akka cluster in order to simulate huge load against our service, we can do it just like this, sending messages to the shard region. And that takes the picture from this to approximately this. I've taken a couple liberties here, but you can think of it logically like this. So now we're running under the cluster guardian actor, because these actors are going to be distributed in the cluster, not just locally. And we're taking advantage of the cluster sharding capability. And the cluster sharding is going to supervise all these shard regions and distribute those shard regions evenly across the cluster. And then under each shard region, we're running these supervisor actors, and then under that we see the actors we saw before, the BACKOFF supervisor and ultimately the wind turbine simulator actor that's running the streaming workload. And these can get distributed logically in an Akka cluster, and you don't really have to care about where the actor is actually being placed. Let's take a look at a demo. So this is a 3-node cluster. Each node's represented by a tile, and these are those simulators that are emitting a new message once a second, and the service is just echoing back whatever message it got and then printing it to the screen here. And I highlighted one simulator in yellow so that you can follow it on the right-hand side there. And then I'm going to kill the node on the right-hand side, and you'll see the cluster is going to talk and determine membership for a second or two, and then you're going to see that simulator come back to life in yellow on the middle node there. So we don't even need to take any action in terms of keeping our simulators alive here, even with a node failure. And you'd have a similar experience, too, if you scaled your cluster dynamically by adding nodes to it and that kind of thing. All these actors are going to rebalance, and the streaming workloads that they're running would rebalance with them. OK, now that these actors are running all over the cluster, what if we want to send queries maybe to check, is that simulator running? Or maybe you want to inject messages into our simulation to simulate faults or change behaviors or those kind of things. So how do we actually reference one of those streaming workloads? Well, we can basically send a message all the way down through the shard region, all the way down to our wind turbine simulator. And I'll just zoom in on the receive of the wind turbine simulator and just implement a trivial example. When the wind turbine simulator gets a message saying, hey, what's your actor path? It'll just respond with the actor path. But of course, you can imagine something like returning intermediate results or stopping this current simulation or all sorts of things like that. And in order to talk to this actor that's running in the cluster, and we don't even need to care where it's running. All we need is the ID, and then we just send the shard region a message. And we'll receive a response just like we would talking to an actor. And of course, we could host this in an HTTP route if we wanted to expose a web service that maybe someone could call to make a similar query. OK, to finish, I want to blur the lines just a little bit between actors and streams. So what about persisting a streaming workload using an actor? Now, we saw in the introductory example that this is a bad idea, right? You don't have back pressure with actors, you have unbounded mailboxes, you have to worry about memory, all these kind of things. But I want to revisit it in terms of Akka persistence. So let's return to the wind turbine simulator example one last time. And I'll talk about one more example that would be a diagnostic event. Let's say we can trigger a diagnostic event that it's short-lived, it sends some high-resolution diagnostic information to the service over the WebSocket and then completes the diagnostic event. And each diagnostic event is going to have a unique ID so that we can look back on it for operations or maintenance or something like this. So when we create the WebSocket for this diagnostic event, it's going to just send messages to an actor that's going to manage the lifecycle of the diagnostic event. And it's going to use the ask pattern like we saw before, so it's back-pressured and safe. And when we create that WebSocket, we're also going to create the actor that's going to manage the lifecycle of that event. And this actor is going to be a persisted actor using Akka persistence. And the ID it's going to use for the persistence ID is the ID of this unique diagnostic event. And when it receives new events, every new event it's going to persist into a persisted journal. And this is a much more stripped down version of Akka persistence than you would normally see. What I want to focus on here are just the streaming aspects of Akka persistence. So what this looks like visually is as these events are coming in through this persisted actor, they're being persisted in order in this persistence journal. You can think of it like a mini Kafka almost, where you have your topic is your diagnostic event, and you can get the full history of what's happened in that event. And of course, you could have thousands or millions of these events stored on disk. In terms of what you use for your persistence journal, there's a bunch of different ones out there. Cassandra is a very popular choice because of its read-write scalability as well as its durability. And you could essentially persist these events forever as long as you're comfortable keeping that amount of data on disk. Now let's take a look at querying those persisted events. And this can be done using persistence query, which is part of the Akka Streams API. And what it allows you to do is basically take those events that were persisted by an actor and then stream them out of that persisted store. And the only thing that you need to do that is the persistence ID. And then you can create a stream that's going to start admitting events from the journal in order. And there's two ways to emit these persisted events. The first is a query that goes from a certain offset to another offset and then completes the stream. And of course, you could host that in an HTTP service again if you want to create a web service to allow clients to make that query against a cluster. Or if the query is, say, too big and you need to introduce pagination, you could also use the offsets as some kind of bookmark so that you could paginate the request. There's also perhaps more interesting is a query that you can hold open. So again, it's from one offset to another offset, but the stream is not going to complete. And the stream is going to continue to emit new events as they're persisted into the journal. This is usually implemented by polling in the background. But with this, you could implement something like a WebSocket stream that's going to emit new events as they're persisted into that persistence journal. And interestingly, we also have location transparency, something usually associated with actors. We actually now have it for streams through Akka persistence, because the only thing we need to stream these events back is the persistence ID. We don't need to care where that actor's running in the cluster. In fact, we don't even need to care if the actor's running. The diagnostic event could be long over, and we can just stream events back from it. OK, summary. So in terms of actors, you've seen that they're great for managing state, for managing lifecycle. They provide a great concurrency model, really useful for distributed computing. They're queryable, something that streams aren't. And they provide location transparency in terms of those queries as well. And they're very useful for modeling, things like I think GE coined that term in terms of digital twin, but being able to represent a customer or an order or a wind turbine using an actor as its digital twin. In terms of streams, they're great for streaming workloads, of course, and they provide back pressure, which gives us bounded resource constraints, and it allows our systems to handle dynamics in a really elegant way. And the semantics of Akka streams are super, super powerful. Probably deserves a whole talk on its own. But they take extremely challenging things to implement and make them very, very easy and very, very testable. And I think you can also start challenging some workloads that you don't think of as streaming and start recomposing those using Akka streams in quite a few places. And of course, together, streams and actors really let us handle fast data and complex state at the same time as giving us location transparency. And that really allows us to build these systems that can handle telemetry as well as asset metadata and complex relationships. And it can do so in a composable and extensible way, too. It's one of the great things about Akka is it's a toolkit. You can slowly pull in what you need, especially as your application evolves. It's not dictating that you have to use it all in the beginning. And Akka is really something that can grow with you as your applications grow. And it's also great for integrating with other systems, which not all streaming applications are. We've seen here, we saw a connection to Kafka through the Alpaca project, and we've seen lots of HTTP. Akka and Akka streams are great living in these ecosystems that have lots of other systems around them. And so great for building reactive streams, or reactive systems and reactive applications. And to close, I want to pick up on what Mark Burgess said yesterday. I really enjoyed his keynote. And certainly when we can build simple systems, we should build simple systems. But I think I liked his message that some of those systems at the core of our business are kind of inherently messy, and that's not all a bad thing. And I think Akka and Akka streams deal really well with those systems that are operationally challenging, maybe doing distributed control, those kind of things. They help tame some of that, some of the complexity, some of the intellectual challenge in building those systems. But they can also kind of deal with the messiness of working with all those disparate systems. So yeah, a lot of examples. Where'd my slide go? Here, if you want more detail on a lot of the examples that I provided here, you can refer to these blog posts of mine. If you want to study them in more detail, that's me on Twitter, and I think we actually have time for questions. No questions.
Yeah, I have a question. That was a nice talk. Thank you. So I have a question about Akka event sourcing, for example. All the talk about what's that, back pressure. So I'm actually thinking, if in a simplistic scenario, if you are again talking about persistent streaming, or stream persistent, or persistent streaming, or whatever, that kind of undermines the fact that you really want to do things in real time. And you are actually adding one more layer of persistence. If you actually tackle that challenge there, you can actually do a lot of concurrent, scalable distribution by just scaling up any of the existing message frameworks. You can basically have a distributed system where you can actually pull on demand, which is really the back pressure, really, because the source is always persisting, and you basically pull what you really want.
You can. It totally depends on the latency requirements of your application.
So that the whole back pressure is actually, in a way, you can actually simulate it in another way. You basically pull at your own speed. Would it solve the problem?
I don't quite follow your question.
I think the persisting, what is that called? Persistent streaming or streaming persistence, or what?
Akka persistence?
Akka persistence, yeah. So that's the kind of contention I have. I think I can follow up to that point, but once you persist that, you have like Cassandra or some other distributed way of persisting the stream that actually comes from your turbine, right? And then when you have a stream persisted there, then can't you actually solve the problem of back pressure by just pulling on demand?
There's back pressure. You can have back pressure through that. There's back pressure in the example that I described. And if you're not comfortable with if your application can't handle that latency, I mean, it is fairly low latency anyway, but if that's still too much latency for your application and it needs to be memory-based, sure. It's just about the trade-offs that you need to make in your application.
Yeah.
And there's no reason why you can't do both. Right, you can actually persist, and you can actually.
That's what I see. The industrial use should be actually a mixed case of.
Yeah, you're not limited to choosing one.
Right. Thank you.